All right, so thanks again to Lander, and our final speaker before the BOF and poster session is Joey Tindall, also from the Flatiron Institute, talking about some very exciting recent results related to simulation of tensor network states, also related to a claim of quantum utility. So get excited, everybody. Go ahead, Joey.
Thanks. Is this, maybe this isn't working, I don't know.
Yeah, I don't think the clear works.
Okay, cool. Yeah, thanks. I'll try to keep it within time just so that, I'm sure we're all tired. So yeah, I'm a researcher at the Flatiron Institute, and I'm going to be talking about some recent work based, again, on the ITensorNetworks ecosystem, some code we've been developing, and then an application of that code that happened very recently towards a recent Nature paper by IBM. So these are my collaborators. So Matt here gave a talk earlier, is a research scientist at CCQ, and there also have Dries and Miles, who are also at CCQ, who collaborated with me on this project. And sort of, we've heard it already, so this kind of research was done within the ITensorNetworks package, which is a package for sort of optimizing and performing contractions of general tensor network structures of arbitrary geometry. And the idea is that you can just define a graph object, and then you will build your tensor network based on that graph object and can manipulate it using graph-based functions. And this kind of keeps track of all the indexing and the location of the tensors for you, so the user doesn't have to worry about that. And today I'm going to be talking about a specific kind of thing that you often might want to do with a general tensor network, which is to basically just evolve it in time, or to apply a series of two-site gates. So you have your arbitrary tensor network, and then you have a series of two-site or one-site gates that you want to apply, and these gates either act locally on a single site, or they act between pairs of sites of the tensor network that share an edge. And this is a very common sort of thing that you want to do with tensor networks, because if you're talking about, say, a many-body system, this is what it looks like to run a circuit on top of that many-body system, is you're applying a series of local gates. So this is a way of simulating a quantum computer, essentially. And the point here is that we're not using an MPS. This could be any general tensor network. It could be a tree, any geometry that you would like to specify. And so what you want to do is you have some region of the network, a pair of tensors, where you want to apply this gate. And generally, this is going to grow the bond between those tensors by a factor of r, which is the rank of the gate. And this is going to grow exponentially with the number of gates that you apply. And so you need to truncate this back and make a truncation and approximate the application of this gate to your tensor network. And there is a sort of exact way to describe this, and that is that you want to essentially maximize this tensor network here. So you contract the whole network down into the region where you're applying the gate, and you need to maximize its overlap with this new approximate tensor that you have and this gate. So this is quite a complicated object, but in principle in ITensorNetworks, we can just form it by just taking our tensor network, applying the gate, and just asking the code to give us this whole contracted network. But the problem is that creating this contraction, this giant gray environment, is something for a general network that is extremely costly and is going to grow exponentially in your network size. So unless you're working on a tree, you need to make some approximation for this environment, typically. And the idea is that in ITensorNetworks, we kind of have all the tools to make these approximations, and we're building up the tools to make these approximations. So like I said, the first thing you can do is you can actually just contract the whole thing and get the full rank environment. And if you have a small enough network, this will work. But the bigger your network gets, the harder this gets. But you can go to the other extreme in ITensorNetworks, and you can actually ask to essentially approximate the environment as an outer product of a load of rank 1 environments coming from different edges. And ITensorNetwork has the capability to do this very efficiently. And on a tree, this will be exact. So on a tree, this works exactly. And this rank 1 approximation is all you need. But on a general loopy network, this typically will be an approximation. It will be more severe the loopier the network and the less tree-like it is. So in ITensorNetworks, we're also developing methods that sort of go for an intermediate rank approximation by using sort of things like generalized belief propagation and boundary matrix product states, and kind of interleaving those concepts. And this is still very much in active development. But today I'm actually just going to talk about this rank 1 approximation, because it turns out that there are certain cases, even not on trees, where it can actually work extremely well. And to sort of introduce a good way to visualize this rank 1 approximation is to introduce a gauge for a tensor network, which we call the Vidal gauge. And it's essentially just a transformation, so you preserve what the network is actually representing, but you make a transformation on the edges and you build in these bond tensors on the edge of your network. And this tensor network then satisfies certain isometries on the edges, so there are certain conditions that the tensors satisfy. The details aren't particularly important. But what you then find is that these bond tensors are essentially form a rank 1 approximation of the environment. So if you find these bond tensors, you found that rank 1 approximation everywhere in the network. And in ITensorNetworks, we essentially have implemented a very efficient way to take a general tensor network on any geometry and just transform it into this gauge using belief propagation. So there's a belief propagation backend in ITensorNetworks, so the user doesn't have to see it if they don't want. But it's there, and you can just give it a network, and it'll put it into this gauge for you very efficiently. And some code showing doing that on a 4x4 grid is there in sort of 5 lines. And then once you have this kind of Vidal gauge network, then it's easy enough to do this kind of 2-site gate application that I was talking about using a method known as the simple update procedure, which is kind of detailed here. And again, this is built into iTensors. You give it the gate, you give it the network and these bond tensors, and it'll immediately update the network for you based on how much you want to truncate that bond. And we generally find that our method for gauging a network is faster than existing methods. We benchmarked it against some other methods in literature in ITensorNetworks and generally found it's more efficient. And we also kind of did a lot of work where when you do this simple update procedure, we find that it tends to spoil the Vidal gauge a bit, so you have to keep re-gauging the network after a certain number of gate applications. And so we did some benchmarking to kind of show how important it is to keep re-gauging the network after a certain number of gate applications to keep up the fidelity that you get when you're approximating the real evolution. So this is all things that have been implemented in ITensorNetworks and you can play around with. And it kind of fell into our hands a bit that there was quite a recent Nature paper by IBM in which they sort of claimed that they'd simulated a dynamics problem in many-body physics that existing computational methods couldn't keep up with their quantum computer, and they had to run things on a supercomputer, and using tensor networks basically just didn't work for the problem at hand. And so we kind of tried to solve this problem ourselves because our code is very flexible and set up to do this. And what this problem consists of, this is the layout of the IBM Eagle processor. It's 127 qubits. They interact along these edges, so you have these short-range interactions where you can apply gates. And it's got these kind of big loops. And what they did is they evolved this system so all the qubits polarized in the up direction, so pointing in along one spin axis. And they applied this unit tree. So this unit tree consists of like ZZ rotations and single-site X rotations. And they repeatedly applied layers of this unit tree as 2-site gates to this initial state. And these 2-site gates are Clifford gates, which makes them tend to be more accurately implemented by the IBM quantum processor. And what they showed is that when they do some noise extrapolation techniques, that the results they get when they simulate this system are very accurate. And so in a regime where they can kind of verify the results against some exact light cone-based techniques, they get these blue data points which kind of sit close or onto the exact result, whilst when you use something like a tensor network in pink, it falls very short and it appears to fail even for very short circuits. And then they moved into a regime where you can't get the exact result, but you can kind of, there are certain points you can verify, like up here at theta h is pi by 2, this answer should be 1, and their quantum computer shows this, whilst the matrix product state techniques fall short and really can't capture some of these expected features of the model. And this was their claim that they had done something useful on a quantum computer that you can't do on a classical computer. So what we did was take this processor and essentially map it exactly to a tensor network that looks like that processor. So we constructed this tensor network in ITensorNetworks.jl. And it's very simple to do this. So here's the code that we do it. Essentially, there's just a function here, which is a function in name, uses functions in name graphs, and it builds this graph. So it makes a hexagonal lattice, decorates it with some extra qubits, adds a couple of qubits on the end, and then you have the IBM processor. And then we initialize our state just by making an ITensor network over this grid, and pointing all the qubits up. And then we build all the relevant gates to propagate the system in time. We time evolve, so we run over a number of Trotter steps. We apply the gates using the simple update method. We gauge it if we feel it's necessary to gauge the state because we've spoiled the isometry conditions too much. And then we take expectation values under the assumption of these rank 1 environments. And what we find is that in this verifiable regime, we are able to get results that are astonishingly accurate. So for example, here, they are within 10 to the minus 14 of the exact value, and it runs within sort of like a minute on a laptop. 40, requires almost no RAM. And even for these kind of higher weight, tougher observables, we get accuracies on the order of 10 to the minus 7 with very moderate computational resources. And then when we move to this unverifiable regime, we also capture all of the expected kind of features, where like the saturation to 1 of this observable, and we're able to extrapolate our results to infinite bond dimension. So we kind of get this very smooth curve here, which we are still working on verifying that this is probably the true result, which will we'll update the archive with that in reasonable time. So we find this method works really well for this problem. And something very strange is happening, is because we're making quite a severe approximation that the environments are all rank 1. And for a network which has loops, this can be a very severe approximation and a poor approximation. But what actually happens is if you look at the system for, say, 1 loop, and you compare the results from our BP method to exact, you see that after about 6, 7 Trotter steps, the true result and the BP result completely diverge. The environments are not rank 1. And this can be seen by the kind of gap in the transfer matrix basically closing. But what amazingly happens is as you increase the number of heavy hexes, this approximation becomes less and less severe, and this gap suddenly stops closing. And we have results going to further system sizes, which actually suggest that it really doesn't close at all, and that as you go to a big enough system size, the model actually behaves like a tree, even though it's not on a tree. And this rank 1 approximation is really accurate. This is what we see in our numerics. We don't entirely understand it, but it is what we see, and it explains why our method works so well. And I should also finally point out that we aren't the only ones that kind of published classical results on this IBM experiment following its release. There were methods from other groups based on truncating large Pauli strings, doing much smaller systems, and using MPO techniques, which also showed that they can also simulate the system to quite reasonable accuracy with moderate resources. And at the moment, we're kind of working on showing exactly how accurate our belief propagation method is and why we think that kind of in this disputed regime, our belief propagation results might actually be much more accurate than we first believed. And as just to summarize, this was all done and made possible through the ITensorNetworks package, which meant like almost all of the code had already been written. It was just a matter of creating a short script based on this exact problem to deal with it. And yeah, thank you.
So thanks very much to Joey for the awesome talk to sort of end our session today. So as you can see on the schedule, we're supposed to have Quantum BOF right now, but as you probably heard, there's a bunch of people going out there for the poster session. So we were thinking we'd have the Quantum BOF directly outside the door within striking distance of all the refreshments and stuff. So let's thank Joey again. If you have any questions for him, I'm sure he'd be happy to answer them maybe after he gets something to eat.
Sure.
And we will reconvene outside. The BOF was not supposed to be recorded anyway, so let's also have a big shout out to our AV folks who helped us out today. And just also a huge shout out to everybody who attended all the talks, for all the great discussions. Thanks again for coming. I hope this was valuable for people attending JuliaCon too. and have a great rest of the conference.